Moving on to milestone 2, we will now be talking about the inverter. We used a traction voltage source inverter to supply the motor with a steady AC voltage output from the battery. We will be discussing topology, calculations, component losses, and output. Looking at our circuit, the first leg of the diagram is a boost converter. We use the boost converter to take the 400 volt battery and output a stable 600 volt source for our inverter stage. The boost can account for any slowing of the inverter's response time due to any fluctuations in the battery as it may be charging or discharging. If the boost stage was removed and the battery was directly connected to the inverter, it would result in overmodulation. Overmodulation maximizes the phase voltage, and in the presence of non-ideal components, such as the case of diode voltage drops and switching resistances, this would reduce the output voltage and the controls could not adjust the output any higher as they are limited by the losses. The controls for the boost converter involve a duty cycle input, which was derived from low voltage battery side at 400 volts and the desired high voltage output at 600 volts. This duty cycle inputs a PWM generator, which controls the switching time of the MOSFETs and diodes. We have 2 parallel MOSFETs and diodes instead of the usual 1 each due to the high current demand of the system. Moving on to the inverter section, we chose a 3-phase inverter to supply a stable 396 line-to-line voltage. Looking at the inputs, we have a control voltage comprised of a sine wave at 60 Hz combined with a modulation index of 0.76. This modulation index was achieved from the line-to-line and subsequent phase voltage. We compare this control voltage with a triangular waveform to control whether a signal is relayed or not. When the control signal is greater than the triangle wave, a signal is relayed to a switch on. When the opposite occurs, the switch shuts off. There is a NOT control system in place to make sure the MOSFET in series is off while the other is on to avoid a short circuit. The remaining 2 legs of the inverter share the exact same controls as the first, except they are phase shifted by 120 and 240 degrees respectively to properly maintain a 3-phase output. This takes us to the final leg of the inverter at the delta arrangement. This last leg takes the output of the inverter on an equivalent RL load that represents an induction motor. This output results in a moving sine wave which can be seen in the voltage and current readings. This equivalent RL load was calculated using our given power at 358 kilowatts, our rated voltage at 396 volts, and a selected power factor of 0.9. Using the equation for 3-phase power, the RMS phase current was derived to be about 1,740 amps. Using this value, the delta load was derived in real and imaginary components, with the real portion representing the resistance and the imaginary being derived into an inductance. Here we can see the voltage output, and if you look between the 3 legs, the average would end up as a sine wave. The same can be seen in the current output. Taking a quick look at ratings, on the left side we have all the calculations used to design our inverter. On the right, which we will discuss shortly, are all our calculations to discuss power loss. The same was done for the boost converter. On the left, all the calculations to design the converter, and on the right, all the calculations for the power loss. Now we will look at component losses, starting at the boost stage and the switching losses. This MOSFET in particular was selected for this case. From what we already know about the boost converter, the RMS switch current is 516 amps, the on-state switch current is 897 amps, and the off-stage switch current is 892 amps. Looking at the chart, we can find the corresponding switch losses in millijoules. Using these obtained values, we can then calculate the conduction and switching losses for the MOSFET, and the sum will be multiplied by 2 for a total of 1600 watts. We multiply by 2 as there are 2 individual components in the circuit. Next, we will look at the diode for the boost stage. Similar for the MOSFET, all of the information needed can be calculated from what we have calculated for designing our boost converter. Repeating the same steps as before can get us our total power lost. For the inverter, it is a repeat of what we just went through in the boost stage, but with a new set of characteristics. Here's the MOSFET, and here's the diode. From what we just discussed, we were able to find the total power loss for the boost stage and the inverter stage. We can then calculate the efficiency using our motor power and our total power lost, and we can combine for a overall efficiency of 87.62%.